Thank you. Thank you for the nice introduction. Well, thanks to all of you for being here till the very last talk. I really appreciate. And as the last speaker, I think I have to really thank the organizers for the great job they did. So I think we, on behalf of all the participants. Okay, so this is the title of my talk. And but what I'm going to discuss today is actually a physical phenomenon that probably most of you have encountered at some point in your research. That is metastability. So the picture you should have in mind when thinking of metastability is some potential or some free energy landscape where you have some local minimum and your system is stuck in a local minimum. And this may happen in many different areas of physics. First of all, this is what I would call a metastable state or false vacuum, so set the terminology. And so, for example, supercooled or superheated liquids. So, of course, in condensed matter, basically every time you have a first-order phase transition, you have some kind of metastability. It is actually an interesting problem also in high-energy physics. So, people trying to understand if the standard model is metastable. We've heard about metastability on Louise's talk on Tuesday. So, okay, this is a very, very general question. And what one typically expects is that if you have a metastable state, then because of thermal or quantum fluctuations, this metastable state will decay to the true vacuum, what I would call the true vacuum, or the global minimum. And I will focus in particular on the decay triggered by quantum fluctuations. Now, the simplest example where you can actually compute this decay rate, so the probability to decay per unit time, is in quantum mechanics. It's a standard textbook's problem that is tunneling through a barrier. So if you have a single particle and you want to compute the tunneling rate, this you can do with a semi-classical approximation. You get the rate as this expression, so it's exponentially suppressed in this quantity that depends on the height of the barrier. Now, okay, now this works really well. You will see this kind of functional forms throughout my talk, but this is actually too crude to describe most of the physical questions that we're interested in, so actual many-body problems, because we need a model that takes into account some spatial inhomogeneity. And let me mention that there are more, of course, there are methods to do this, especially like people study this in quantum field theory using again semi-classical approximation and instanton calculation, but I will not go into this. But let me try and give you a physical picture of what I mean here with spatial inhomogeneity. So what I really mean is that this tunneling process happens through the nucleation of bubbles. So here, for example, this is some numerical simulation for a system of cold atoms. And what these people studied was that essentially if you start from a system that is in a false vacuum, okay, so yellow is false and blue is true vacuum, what you find is that at some point you will form some bubbles, and if you have some large enough bubbles, one such bubble can expand and eventually trigger the decay, and will essentially enlarge till it covers the whole system. Now, the theory to describe this bubble nucleation, like the important aspect that one has to keep in mind, is that the energy of a bubble has two contributions. So creating a bubble lowers the energy. So there's this negative term here that's proportional to the volume, simply because true vacuum has lower energy than false vacuum. So there is this volume contribution that's negative, and there is a positive contribution that's proportional to the area of the bubble, so to the surface. This is surface tension, essentially. And so this means that if you want to trigger this false vacuum decay, you need to reach a certain size for this bubble, a critical size, such that this energy is negative. Okay, so if you're able to tunnel to create a bubble that is large enough to achieve this condition, then you will observe this kind of phenomenon. Now, yeah.
So, I mean, when you did tunneling preserves energy, so you can also tunnel back. Why is this not happening why is there no inverse bubble created?
Yeah. Okay, very good. Yeah, so in that specific example, the idea is that what's happening is that once you tunnel through, essentially what happens is that this bubble can increase their size, so it's lowering the energy, but there's essentially kinetic energy that's being used. So the walls can accelerate, and this is where the energy is going. You could have also the process that goes back, but it's much more unlikely in a sense. But actually, what I will describe later, it will be different. So, okay, so one question is, how does bubble nucleation occur in real time, like in real-time dynamics? Because, for example, the semi-classical calculation that I showed earlier are based on this path integral formulation. They don't actually describe the actual formation of bubbles and their correlations. So this can be, in general, a difficult problem because this is a problem of non-equilibrium dynamics of a strongly correlated system. So typically, this is difficult for traditional analytical or numerical methods in some cases. And so this would be one example of a problem where quantum simulators could be some promising applications. So in general, quantum simulators will most likely be good at trying to understand non-equilibrium dynamics of many-body system. But let me explain what I mean by quantum simulators. So quantum simulators, where we have already heard about this in some of the previous talks, and these are systems, so there are some experimental setups that can be easily controlled. And for example, some ultra-cold atoms in optical lattices, or systems of trapped ions, like Rydberg atom arrays, superconducting qubits. So these are all systems. These are truly quantum many-body systems that can be manipulated, and those parameters can be tuned. This is sometimes called like synthetic quantum matter. And as was already explained, I think, some of the talks on Tuesday by Pablo and Vir, this was basically one of the motivation for studying new questions in non-equilibrium dynamics. And the reason is that the non-equilibrium dynamics that you can realize in a quantum simulator, like the natural kind of dynamics that you can typically have, is the following. You prepare some initial state, some pure state. Then the system will evolve unitarily. You can, for example, have some Hamiltonian evolution. You can have evolution like digital with gates. And in the end, you get some final state that will be pure if the system is actually unitary. And you will detect the final state. And so this is quite different from what people typically studied in non-equilibrium dynamics of like condensed matter or real materials. And in fact, this essentially motivated much of the work in the last 10, 20 years in studying thermalization and quantum chaos, and essentially this kind of questions about isolated quantum many-body systems. Okay, so these are the kind of tasks that can be naturally realized in quantum simulators. So can we observe the false vacuum decay in this context? So this is the motivation for what we studied. And so the focus of this talk, what I'm going to present next, is the following. We will study some quantum spin chains, in particular quantum Ising chain. And the reason why we study this is that, well, this can be implemented with some of these quantum simulators, but I mean, I'm a theorist, so I want a model where we can have some semi-analytical results that we can compare and also some numerical methods where we can compare the predictions of our theory. So I will focus on these models, and I will focus also on protocols to study this in this kind of non-equilibrium dynamics. So this is the outline for the rest of my talk. I will first introduce the model, so quantum Ising chain. I will describe how bubble nucleation occurs, like how it happens in these models. Then I will introduce the protocol and show you the results. And finally, if I have time, I will say a few words about about the excitations in this model. Okay, so the model is the following. So it's a one-dimensional chain, spin 1-half. So there's a ferromagnetic ZZ interaction, and there's a transverse field. And okay, it's well known that if J is larger than the transverse field, then the ground state is ferromagnetic. So essentially, okay, we've seen actually this picture already in some of the previous talks, and you essentially have two ground states. I'm showing them as two minima in this potential that corresponds to all the spin pointing down and all the spins pointing up. Now, in this model, we're going to include now a longitudinal field. And the effects of the longitudinal field is essentially to change the energy of these two minima, so lowering this one and increasing the energy of this one. So essentially, this is how we get a false vacuum and a true vacuum. Okay, so this is if you want, our local minimum where we will observe the decay from. Okay, now, I said the decay happens through the nucleation of bubbles. So what are these bubbles? Well, they're essentially domains so if this is false vacuum, they're domains of true vacuum. This I call L the length of this domain. And so the energy of this bubble is, to some good approximation, you can model it as in this way. So you get twice the mass of a domain wall minus this, which is the energy essentially given by this term, by the longitudinal field. So, and this is M is the magnetization, and L is the size of the domain. And so here you can recognize the formula that I showed earlier, where you have the area contribution positive. So in this case, is in 1D, so it's order 1. And there's a volume contribution that's negative, so this is proportional to L.
So are you assuming the longitudinal field is infinitesimally small?
Yes. So I'm working in that regime where it's very small. Yeah. Okay. So then, what is now the picture for this bubble nucleation? Well, to go from the false vacuum to the true vacuum, you first have to essentially, you can only flip spins locally. So in some sense, what will happen is that you first have to flip a single spin, which means you increase your energy a lot because as I said, this longitudinal field is small, so this mass is much larger than this. So you need a lot of energy to do this, and then but once you do this, once you create these two domain walls, then you can keep flipping your spins without just lowering your energy essentially. So you're essentially going down until you reach a bubble that has the same energy as the state you started from. Okay, and this is what we call this a resonant bubble. And well, from this equation, you can read out the length of this resonant bubble will depend, will go as 1 over hz, where hz is the longitudinal field. And you can, essentially, we're interested in this tunneling process, so between the false vacuum and the resonant bubble. And this tunneling process, you can compute the matrix element. So let me give you an argument for why this is the expression. Well, if you think of this as some process in perturbation theory, you have to flip L tilde spins. So it means you have to go to L tilde order in perturbation theory, which means that this matrix element is exponentially small in L tilde. And then if you use this expression, you see that this is exponentially small in 1 over hz. And OK, this is some like rough argument. You can do the calculation, a more serious calculation. This is what was done in this paper with all the constants and all the coefficients. And this is the theoretical prediction that we will compare our results with. OK. So now, what is the Quench protocol? What is the dynamical protocol that we're studying? So we start from a product state, so all spins pointing in the down direction. So this is essentially the ground state of the Hamiltonian with the opposite sign of the longitudinal field and with 0 transverse field. Now, we want to work with some finite transverse field, so we have to essentially, in an experiment, you will slowly turn on the transverse field, or if you, in our numerical simulation, we apply some imaginary time evolution to essentially get the ground state of this Hamiltonian with a finite transverse field. And then we flip the sign of the longitudinal field. So now this one, the state that we prepare is not the ground state, is this false vacuum. And now we let the system evolve with this Hamiltonian, and we see we want to observe this decay. Yeah.
Why did you do the second step?
This one. Yeah, is because okay, so if you don't, you need to have some transverse field for this decay to be there, otherwise the system is trivial. And so, but if you don't, essentially if you don't cool down to the ground state with a finite transverse field, you already have excitations in your system. So you really want to start from the ground state with like the dressed vacuum, if you want. Okay, so these are the results of our numerical simulation. So I will not go into the detail of the method that we're using. But OK, we essentially study various observables and their evolution as a function of time. And OK, also, I don't need to re-explain what these observables are. What is important is that we are interested in understanding what happens. Like, we essentially fit this against this kind of expression, and we're interested in this rate gamma g and gamma f. Okay, so we extract this decay rate from the dynamical results. And okay, and this is what we get. So these gamma g and gamma f are the ones we extract from those fits. Here we plot them as a function of 1 over hz for different values of the transverse field. And this pink line is the theoretical prediction. And so you see that in all these cases, we see some straight lines, which means we have, this is a log scale on the y-axis, so it means that we have this kind of dependence, e to the minus 1 over hz, which is the one that that I showed earlier. And the slope also agrees with the theoretical prediction, but not the prefactor. So what you can see here, for example, is where we really plot just the slope of these curves. You see that they all match very well with the theory. So it's okay. We find agreement in the exponent, not in the prefactor, and this is actually, we believe there's some interesting physics here because even different theoretical predictions don't agree on the prefactor. So if you like field theory calculations show a different prefactor than the one that was predicted here. So I think this is something interesting that needs more investigation. And another thing that we wanted to do is to see, okay, is this just something that happens for that specific model? It's very simple, quantum Ising chain. What if we try with another model? And for example, we studied an XXZ ladder. And here, this, okay, you don't need to know the details of this model, but what is important is that this coupling delta perp plays the role of the longitudinal field, is the one that's explicitly breaking the symmetry. And yeah, and so we do the same thing. We look at the decay of some observables in time. We extract the decay rate, and we find the same kind of dependence that we had in the other case. So this gamma depends on delta perp through this expression. Okay, so this is essentially, oh yeah, sorry. one last thing I forgot to say here is that here you see actually that these are not really straight lines. You see some kind of oscillations, and we actually, this is something we're studying right now. What is the origin of these oscillations? And we know that this the origin is that well, some excitations are produced in the quench. So even if what you prepare is very close to the false vacuum, still you can essentially have that. You know, if you quench, you still have some excitations, like some oscillation, if you want, around that minimum. You can think of them as some local excitations. And the interesting thing is that if you do this, if you study this quench for the different signs of the longitudinal field, you can actually extract the spectral properties of the excitations, and you can find like different properties in these two cases, and you can learn a lot about the excitations of the system. Okay, so to summarize, metastability and false vacuum decay describe a variety of physical phenomena. They can be studied with quantum simulators using like these Quench protocols, so non-equilibrium dynamics. We studied a quantum Ising chain, and we find some partial agreement between the theoretical prediction and numerical results. And in this quench, some excitations are produced, and they can be probed with a spectral analysis of these oscillations. Now, I think some interesting direction for the future would be to study eventually like the real-time dynamics of bubble really in space. So we only focus on the decay rate, but there's much more than this. There is correlations of bubbles and all this non-trivial special structure of this bubble nucleation. We haven't looked into that, but there are some interesting works on related questions that use some matrix product states techniques to study this. Of course, it would be interesting to actually observe this in quantum simulators. So this is, for example, a recent work where they studied this in a cold atomic gas. This is actually induced by thermal fluctuations, and they observe essentially the formation of a bubble in the system. And of course, as I said, there are some open questions about the prefactor and what is the correct way of getting an estimate of the decay rate. So with that, I want to thank my collaborators on this project, especially Gianluca Lagnese and Pasquale Calabrese, and I thank you for your attention.